But they detected it in a very narrow band of frequencies, and that makes it it cannot be through natural processes, a very narrow band, just like some radio transmissions that we produce. But if it were to come from the habitable zone, from a transmitter on the surface of Proxima b, this is the planet that orbits Proxima Centauri, then I calculated that the frequency would drift through the Doppler effect. Just like when you hear a siren on the street, when the car approaches you.
Imagine a world orbiting the closest star to our solar system, where liquid water might flow, yet unyielding radiation threatens to strip it bare. This is Proxima b, a planet that challenges our understanding of what makes a world habitable. The discovery of Proxima b, a rocky planet circling Proxima Centauri, signifies a major milestone in the quest for potentially habitable worlds. Its fascinating position in the habitable zone of its host star suggests that liquid water could feasibly exist. However, habitability is not solely determined by location. The planet's capacity to support life is heavily influenced by the intense radiation it receives, spanning X-rays to ultraviolet and infrared light. Understanding this radiation is crucial for evaluating whether Proxima b can maintain an atmosphere, sustain surface water, or even host life. This exploration has two primary objectives. First, to investigate the radiation environment of Proxima Centauri and quantify what reaches Proxima b. Second, to refine our understanding of Proxima Centauri itself, its mass, size, temperature, and brightness, as these factors shape the planet's potential for habitability. By integrating observations across various wavelengths, from X-rays to infrared, this research provides a detailed look at the star's emissions and their impact on Proxima b. Proxima Centauri, located just 4.24 light-years away, is the closest star to our Sun. As a red dwarf of spectral type M5.5, it is significantly smaller, cooler, and dimmer than the Sun, possessing only 12% of the Sun's mass and 15% of its radius. With a surface temperature of about 2,800 K, Proxima Centauri's light output shifts toward red and infrared wavelengths. Despite its dimness, its proximity makes it an ideal candidate for detailed study. Proxima b, the star's closest known planet, orbits at just 0.485 AU, closer than Mercury's orbit around the Sun. Yet, because Proxima Centauri is so faint, this distance places the planet within the habitable zone. Proxima b receives approximately 877 WM2 of stellar energy, roughly 64% of what Earth receives from the Sun. However, Proxima Centauri's intense activity, characterized by frequent flares and strong stellar winds, raises critical questions about the planet's ability to retain an atmosphere and sustain life. Mapping Proxima Centauri's emission spectrum is essential for understanding the potential habitability of Proxima b. The exoplanet is known for its variability, particularly in the form of flares that significantly increase levels of high-energy radiation, such as X-rays and extreme ultraviolet radiation. These stellar flares are much more frequent and intense than those of our Sun, potentially having a substantial impact on Proxima b's atmosphere. The planet's close orbit around its star exposes it to considerable radiation. While the star's output is much lower than that of the Sun in terms of visible light, its heightened emission in the XUV spectrum has important implications for atmospheric chemistry. High-energy radiation can break apart molecules in the atmosphere, leading to the loss of lighter elements like hydrogen over time. This could result in atmospheric erosion, especially if Proxima b lacks a strong magnetic field or a protective thick atmosphere. However, the radiation intensity isn't solely a threat. In combination with thermal radiation in the infrared, the energy input from Proxima Centauri also has the potential to shape the planet's climate. Infrared radiation from the star warms the planet's surface and atmosphere, influencing the greenhouse effect, which in turn affects the planet's ability to retain heat, regulate temperatures, and maintain a stable climate for potential life forms. The integration of data from multiple instruments helps build a more comprehensive picture of the radiation environment around Proxima b. For instance, by analyzing the star's X-ray and UV flux in detail, scientists can estimate the amount of stellar energy available for atmospheric heating and determine the likelihood of atmospheric stripping. Similarly, observations in the infrared spectrum allow researchers to model how Proxima b might retain heat, especially in the face of intense radiation. Ultimately, these combined observations inform our understanding of how Proxima b's atmosphere might behave in response to its host star's radiation. The planet's potential to sustain liquid water or harbor life is significantly influenced by these radiation interactions. Although high XUV radiation levels present challenges, there may be regions on Proxima b, perhaps in its twilight zone or deeper in its atmosphere, where conditions are more stable and potentially habitable. However, the balance between radiation-driven atmospheric loss and thermal retention will likely play a central role in determining whether Proxima b could sustain life as we know it. To explore Proxima b's potential for habitability, it's essential to understand both the stellar environment it resides in and the evolution of the planet's atmosphere. Proxima Centauri, a red dwarf star, is much smaller and cooler than our Sun, but it is also highly active in terms of X-ray and ultraviolet radiation. This radiation plays a key role in the development and retention of a planet's atmosphere, particularly in the early stages of its formation. Red dwarfs like Proxima Centauri can be very volatile, emitting intense flares and XUV radiation early in their lifetimes. This period of activity, often referred to as the pre-main sequence phase, can last for hundreds of millions to a few billion years. During this time, the intensity of XUV radiation can be many times greater than what the planet would experience today. If Proxima b was exposed to these early bursts of high-energy radiation, its primordial atmosphere, if it had one, could have been stripped away, making the planet less likely to retain water or life-sustaining gases. However, after this initial active phase, red dwarfs like Proxima Centauri typically settle into a quieter phase, where their radiation output stabilizes or decreases significantly over time. This creates a second phase in the planet's history, where the possibility for atmospheric recovery may emerge. If Proxima b experienced volcanic outgassing, where gases like water vapor, carbon dioxide, and nitrogen are released from the planet's interior, this could have helped build up a secondary atmosphere. Alternatively, impacts from comets and asteroids, which could have carried volatile compounds, might have contributed to the formation of a new atmosphere. In addition to the loss of its atmosphere, Proxima b could also face significant challenges due to its proximity to its parent star. Because Proxima Centauri is a red dwarf, Proxima b is likely tidally locked, meaning one side of the planet always faces the star, while the other side remains in perpetual darkness. This could result in extreme temperature gradients, with scorching heat on the star-facing side and freezing cold on the opposite side, potentially complicating the prospects for life as we know it. Moreover, understanding the timing of Proxima Centauri's activity, specifically the transition from an active to a quieter phase, is crucial for determining whether Proxima b's atmosphere could have had enough time to stabilize. If high XUV radiation persisted for too long, it might have prevented the development of a thick, stable atmosphere altogether. Thus, while Proxima b remains one of the most intriguing exoplanets in the search for habitable worlds, its long-term habitability depends on a delicate balance of factors: the nature of its star's radiation history, the ability of the planet to develop a protective atmosphere, and the environmental conditions that may have allowed for the emergence of life. Future missions to observe Proxima Centauri and Proxima b, such as the James Webb Space Telescope, will be key to determining whether the planet's atmosphere, if it exists, could support life. The discovery of warm dust in the system adds another layer of complexity. The 20% increase in infrared emission suggests an additional source of heat, likely due to warm dust particles. This dust is probably heated by the star's radiation, and its presence is unusual since dust in the interstellar medium generally cools and dissipates over time. The fact that it is still present around Proxima Centauri hints at ongoing processes, such as planetesimal collisions or the presence of a debris disk, which are relatively common in young planetary systems, but rare in older ones. The warm dust could have significant implications for Proxima b, the exoplanet that orbits within the habitable zone of the star. If the dust is scattered and absorbed by stellar radiation, it might alter the thermal balance of the planet's environment. For example, it could potentially block some of the incoming stellar radiation, affecting Proxima b's climate and surface temperature. Understanding how this dust interacts with the planet's atmosphere could be key to predicting its habitability, especially when combined with data about the planet's atmospheric composition and magnetic field. Moreover, the presence of this dust raises important questions about the system's architecture. Proxima Centauri's dust may not be uniform, but could instead be influenced by the gravitational forces of hidden or yet-to-be-discovered planets. These planets could be in elliptical orbits or interacting with one another in ways that disturb the distribution of dust and debris. It's possible that additional smaller planets might exist in this system, perhaps on the fringes of detection, whose interactions with the debris disk could be shaping its current state.